All right, everyone. Let's keep talking a little bit. We've essentially, by the time I'm doing this right now, and perhaps by the time people see this, depending on the order in which they see some of the videos, I've already completed chapter 25 of the Katz book, the entire chapter as far as what I wanted to discuss. I was a little, a little concerned about how I handled problem number 30. I think everything that you needed to know about problem number 30 for our purposes is all there in the discussion, part 1 of chapter 25, where I'm discussing these matters. It's all there for you. It's fine. It's a little more lengthy of a presentation than I would have liked to have given, but it is all there for you. That was kind of my concern about it. Let me try to be a little more succinct about the whole process, and maybe bring in some mathematics that I think, once again, maybe it's a little more clear for us. So right now, this is more of a supplemental discussion to things that I've already discussed, and it's going to hopefully be relatively quick when I do it. Chapter 25 of the Katz book, first edition, pertains to Gauss's law, and I'd like to look at problem 30 at some level again for clarification and added discussion. They tell us in problem number 30, let me just kind of flat out read it out, and then we'll kind of just use our own interpretation, or maybe say this in a little different way that might be a little easier to deal with. For problem number 30 on page 782, number 30, they say two very long, thin, charged rods lie in the same plane. One rod is positively charged with charge per unit length plus lambda, and the other, or positive lambda, and the other is negatively charged with charge per unit length of negative lambda. The perpendicular distance between the rods is capital R. Using the coordinate system shown in the figure, sketch the electric field as a function of small r from negative capital R to positive 2 capital R. We've already kind of done this. As I said, I've talked perhaps a little more than I even wanted to regarding the matter, but hopefully there's some method in there when you first saw it that kind of guides you to what I'm trying to say. Let me sort of say it again, hopefully be a little quicker about the whole thing. So here's, as we said, this is Gauss's law and everything else, and why are we reaching some of the conclusions that we're reaching, and what does that mean? And let's see what we can say about it. Get rid of this part and draw the conclusion, I guess, and kind of justify why we reached the conclusion that we had reached the last time that we were together. At least how we were at least trying to verify that it was actually true, that it actually worked. And then we'll see exactly what we want to say a little bit about this. So, I mean, the graph that even the answer key in the Katz book is going to talk about isn't going to be in the most meticulous fashion, but it still gives us a gut feeling for what's going on. And as I said, the first time that I discussed this problem in part 1 of the chapter 25 discussion of the problems, hopefully the basics were brought forward and got us thinking about this a little bit. There was quite a bit of talking about it. Well, I'll talk some more about it. I won't talk as much, I promise. But it's all there, and there's some other stuff that maybe we can look at that kind of gives us a little more insight on the whole matter. Basically, this is R. This is and the wire coming out at us. I mean, but they're both coming out at us in a sense. We're kind of looking at them, getting underneath, and just looking straight across at the wires, and we're kind of catching this. This is for plus. There's no real good way to draw this sometimes, how you're going to draw some of this stuff. That's the plus. This is the minus lambda, the negative lambda. So here's plus lambda to the left, positive lambda to the left, negative lambda to the right. And we said there was a number of things going on. We said, well, we said they're very thin. By very thin, they're infinitely thin. They're at cross-sectional area of 0, I guess you could say. So right when you go right onto the wire, it's undefined. Undefined something huge. Undefined something negative huge, or something undefined something positive huge, but it's undefined when you go there. So with that in mind, we were able to say, okay, we'll say that this right here was height 0 for what E would be. So E equals 0 would be somewhere over here. Again, the way they drew this in the answer key that they have is not the greatest, but it's good. But it's still very good. And I'm not exactly drawing it the greatest either, because I'm essentially following what they were doing here. But it's not bad. What happens is, got something like this, we're claiming. You got something like this going down to very, very negative values. Now look, this E can go way far down. Right here, E is 0, but this can go down to negative infinity. Don't let this solid line have any kind of great relevance. This curve will penetrate through this line and go to an E value of negative infinity. And you got this right here, it'll get closer and closer to 0. This is 0. This is an E field of 0 right here. They didn't really make that very clear. And I also did not make it very clear the last time that we spoke. That's why I want to kind of talk about it now. And again, these aren't, and then we got something like this, going like that. Okay. That's essentially what we're told, and it is correct. Now what's going on? Try to make this thing make a little bit more sense for us, I guess you could say. This thing right here sort of runs the show. And then from here we can do some other stuff to get some ideas of what to do. And I'll try to build on what I built upon last time, or what I tried to say last time. Basically, they're asking guys, and everything what we said last time was correct. Again, it took quite a while, but it's there. It's what we need. Now, you're going to use Gauss's law right here. I mean, that's what this is. And the Fe, the flux, is equal to this, and it's also equal to that, so they're equal to each other. And you're working with this. Well, if you draw around here a cylinder centered at this red one, however big you want to make the cylinder, depending what E field you want to find, we know that the bigger you make, the broader you make the cylinder, the less intense the E field is. The smaller you make the E field, the more intense. The bigger you make, the bigger radius that you make the cylinder, the Gaussian cylinder encompassing this, the bigger that you make the radius of that cylinder, the smaller the E field under consideration, because there's greater distances involved for the E field to be manifested, I guess you could say, for lack of a better way to say it. So a big Gaussian cylinder with a very big radius, the bigger you make the radius, the less intense the E field is. That makes sense. Same with this one. The bigger you make this, the radius of the cylinder, the less intense the E field is. Well, that works the other way as well. The smaller you make the radius of the Gaussian cylinder, the more intense the E field is. And smaller and smaller and smaller, the more intense the magnitude of the E field. It may be an E field going right in toward the red rod, or outside of. Well, it's going to be going outside of it because it's a positive lambda. But here's a negative lambda, and that means it'll be very intense, but it'll be a great magnitude, but it'll go toward the inside. It'll go toward that blue rod because it's a negative lambda. But the smaller that you make the Gaussian surface, the smaller the radius, the more intense the E is. Let's get this straight. Let's build that Gaussian surface over this long, that's very, very long, very thin, infinitely long, likewise here. You've got this, E field coming out perpendicular to the cylinder. The cylinder is 2 pi r in circumference times the length will give you the area that is relevant for us. The cap area is on the side, 0 E field with that, so it's not going to be an issue. E equals, so the side caps don't play a role in that. They're going to be 0 E field. E times 2 pi r L equals Q over epsilon naught. Well, lambda times L is Q. By definition of what lambda is. What's lambda? Lambda is Q over L. Multiply by L on each side, and you got Q equals lambda L. Divide by 2 pi r L on each side. How long is it the length? Make it as long as you want to make it. Very long or very short, doesn't really matter. The mathematics will come out. When you divide by 2 pi r L on each side, you come to here, you got L lambda over epsilon naught divided by 2 pi r L. The L and the L go, you've got this. This one was for the positive lambda. So it's firing everything, the E field is firing out there. Look, this is important. If the radius of the Gaussian surface, small r, is made very, very big, a constant divided by something, lambda 2 pi epsilon naught, that's a constant. That's one big constant. You can put it on top if you want. Lambda over 2 pi epsilon naught divided by r. Divide by r, and if r is very, very large, then the E field is very, very small. Yeah, it makes sense. The further away I get from this thing, the less E field I'm talking about. But it's a positive E field all the time. On the other side of that, if r is really, really small, E is going to be really, really big. Well, how big can it get? Man, we just said these things are theoretically, for our mathematical exercises here, we said they're infinitely thin. So the closer you go toward the wire, without even touching the wire, and it's infinitely thin, you can just keep going closer and closer and closer. R is a tiny number. If that's not tiny enough for you, make it even more tiny. And if it's very, very small, you get a huge answer. So, get really close to this guy, it's a huge E field. Get far away from this guy, it's a small E field. It's the same exact thing right here. Now, it's a little different dynamic. This is a right-handed system. This is 0 to increasing numbers r. This is 0, and these are all positive values. If you go this way, the small r has negative values associated with it. Okay, we'll talk about that in a bit. Right here, let's talk about how this thing plays out, and they want us to know how things play out one with the other. First things first, let's talk about this guy by itself. If you go from here, your distance, well, how far are you from here in this coordinate system? If I go here, from right here, and I go out to here, a distance, well, what is that distance from this guy? It's some value of r. Well, yeah, as this is, for this reference point, 0 to here is r. I agree. From here to here, I don't want to clutter this thing too much, guys, but from here to here is a length r. Yeah, but that I want to know the relation to this. Well, this is r apart. This is big R apart right here. I mean, I know I drew it like this, but maybe it'd be better if I went sideways and drew it. It's neither here nor there, however you want to visualize. This, in reality, is this way. I mean, if we could draw this in 3 dimensions, this is the R, I guess. So this R right here, capital R is this. Everywhere, it's capital R apart. It's capital R right here, capital R right here, capital R here, capital R here, capital R here, etc. We get the picture. Down here too. Capital R, like from here to here, capital R. Okay. From here to here is small r. Yeah, I get that. But how far is it in relation to here? It's this small r, which is a big distance, minus big R, which is a small distance. This distance right here is r minus r. Big R minus small r is what this distance is right here. So, and you can say, yeah, okay, that's great. it was easy to play that game here, guys. Because even in, you got to kind of see there's so much going on here. Where to begin, where to end, I guess you could say this. Let's come back to what we did with the red one, guys. If R is 0, it goes toward infinity. Okay, I get that. If R is a big number, a big positive number, it gets smaller and smaller and smaller. It goes towards 0. It goes towards 0 E field if R is really, really big. Yeah, that's true. If R is, just for this one, for the red one now, if R is a really, really big positive number and keeps getting bigger and bigger, the E field goes towards 0. If R goes towards 0, it goes toward a small number divided into here, and they're all positive. Small number divided into here will give you a big positive number. If you're on the right side of this, it's going to be a big positive number. Forgive me, it's going to be a big positive number on this side if you're on the right side of the red. If you're on the right side of the red, big positive number, or positive number gets smaller and smaller and smaller, it goes towards 0. Very big positive number, as you come this way, moving from the right to the left, and you're still on the right side of the red wire, you're going to get toward positive infinity. Over here, if you go over this way, if R is a negative number, it's going to go toward 0, but it's going to have negative values while it's going toward 0. And when you go toward, for an E field of 0, and if you go toward an R of 0, from negative values, a negative number divided into here is a huge negative number in terms of magnitude. It goes toward negative infinity. So on this side, as you're approaching the red wire, you're going toward negative infinity for the E field. This side, going to the left, you're going toward positive infinity for the E field. Okay, true. For this one right here, as you run this way to positive numbers, you're going to go towards 0. If capital R minus small r is a big number, it's going to go to where you're just going to set it up like this. You're going to say, hey, wait a minute, what's the new radius, the new distance? For the blue, R equals negative lambda, it's this. So it's going to be R minus R, capital R. Forgive me, it's not that. It's going to be small r. It's the same dynamic, but it's going to be capital R minus big R. Now you're probably wondering, what are you talking about? Then why did you write it like this? Why did you write it like this? Well, again, we took the big and we minus the small. The big is small r, and the small is big R. Small r minus big R is going to be that distance right here. Well, that's going to be your radius. You're going to play the same mathematical game that you played here, but you're going to use E times 2 pi, E times the quantity, 2 pi, the quantity small r minus big R times L equals negative lambda. So now I'm doing it for this one now. Equals negative lambda times L over epsilon naught. And this guy right here has to be good enough. Now what happens? Why don't you divide by 2 pi? Oh, there's an L too. There's also an L. Divide by 2 pi times the quantity small r minus big R times L. Divide on each side that, and you end up getting where to go here, guys. Let me take a walk with this guy. Let me go over here, and we're going to find big one minus small one. Yeah, that's the new radius, so to speak, of the Gaussian cylinder centered on the blue wire with negative lambda. Earlier, for the red wire, the Gaussian cylinder was centered on was centered here, and well, it was centered here, and then it was just straight out R. From here, this was your coordinate system where you began the R's, so R became the radius associated with the Gaussian cylinder that was associated with the red wire with positive lambda. So this worked out fine, and that was for the red one for positive lambda. For the negative lambda, you got to make this guy centered, but where is he centered? Well, there's a radius, but the radius in terms of this coordinate system is capital R minus, it's small r minus capital R. That length right there is what this is, R minus R, and that's what I use here. Let me divide by 2 pi the quantity small r minus big R, L, equals negative lambda. So let's see what we got here. We got negative lambda L over epsilon naught. Negative lambda L over epsilon naught, 2 pi times the quantity small r minus big R. Okay, the L's go. You got negative lambda equals 2 pi small r minus big R times epsilon naught. Yeah, I agree 100%. If you multiply top and bottom by a special 1 called negative 1 over negative 1, multiply that by negative 1, multiply by a special 1 called negative 1 over negative 1. Negative 1 times negative lambda is lambda. Negative 1 times all this just reverses these two, and that's where they're getting that. That's where this is coming from. And that's where you're getting this. And that's where we're getting that. I put 2 pi epsilon naught, the 2 pi and the epsilon naught, I put them next to each other, then I have that there. Here I did not have it. It doesn't matter where the epsilon naught is, just have it there somewhere. It's got to be there somewhere to make it work. Okay, that works. It's certainly true. Here's the question, just to kind of watch out when there's all this fancy subtraction going on. We don't have issues with the red wire. The red wire, positive R goes this way, negative R goes that way. Okay, it was believable. You saw me do some arguments related to this in the last video, and you saw me do some arguments more specifically and hopefully more clearly just now related to this. And so that wasn't an issue. This blue one is something I'm a little concerned about. Small r minus capital R will give you anything going this way. Okay, yeah, that's true. That's true. So a lot of ways you almost want to just leave it there. It wouldn't have been a bad idea even to leave it there, to be honest with you, but there's some issue with consistency and how you want the stuff to work. You can argue this so many ways, guys. It's fine as is, actually. So we got this, the way we've done it, the way they've done it. Okay, so we got it right there. What about here? What about in the middle of here? It's still a positive number between here. Between 0 and R, what's going on? Well, let's see what we got here. Well, here, if the length from small r from here onto this wire, small r, is a length of capital R, what's capital R minus capital R? It's 0. Oh yeah, this is 0 distance. Okay, that works. What if here, this is an R, it's an R right here, guys, but this big R is bigger. What is, this is, we got to be kind of essentially, I guess you could say quite careful on this when we do this. We want to see what the distances are under consideration. This is capital R, this is small r. What is small r, which is a small number now, right here in this instance? What is small r, that right there, small r, what is small r minus capital R? It's a negative number. I'm walking in the negative direction. If I'm walking in the negative direction, and there was, like I said, there was a lot of ways. If I'm walking in the negative direction, let's see what's going on here. Well, if you're walking in the negative direction, so r minus r is a negative number, here when you switch them up, it's a positive number. And this is also positive. We're claiming a positive E field then. Well, yeah, if you're over here, this guy pulls you in the positive direction. So it works. It works. It's a bit odd, but it works. We did the thing. We had it up here. It was a little on the odd side. But yeah, this was negative. This was negative. Positive answer? You better believe it. Because it's getting pulled toward the negative lambda. As odd as it looks, it works. It definitely works. What happens if you go this way? What if you go out here, from here to here? What is that distance? Well, that's a negative distance. Well, what is it? It's r, which is a negative number, minus r. It's small r, which is a negative number going that way. Small r, which is a negative number going this way. Small r, negative number going this way, minus a positive big R, which is even more negative. A negative number minus a positive number is even more negative. That makes sense. You want a whole negative distance that way. This also pulls it that way. This also pulls toward the negative. So it's to this negative right here, which means it moves toward positive values. What does that mean? Well, this right here was negative. That was negative. Negative divided by negative is positive answer. Leave positive here. What's a capital R positive minus a negative number? It's a positive answer. Positive divided by positive is still a positive answer, and it works here. So that's a lot of the tug of war that's going on here. We knew that if small r was equal to capital R, r minus r is 0, and man, that blows up everything. That gets us right here. R minus r is 0, and it goes toward positive infinity. There's a lot going on there, you guys. A lot going on there. We want to look at this thing. What about here? How would this guy be equal to 0 at that, or what would be the length here? The length here would be r is 0 minus a big R is negative r. That's still something. Still be a positive answer. You'd have a negative r here, a negative here. Negative divided by negative is positive. Another way you can do it is capital R minus 0 is positive. That's positive. Still gets the exact same answers, you guys. The big thing is this. Wherever the E field is shooting, wherever it's going, that'll tell you if it's a positive E field or a negative E field. So we already said it. And again, I've done a number of things to this now. Hopefully we've got it under control decently. But we know that if you're on here, there's a lot going on here. I mean, is what's going on. I mean, the further away you get from the blue, going in the positive R direction, it wants to draw you back in. It's always everything to the right of the blue. Don't worry about the red right now. In relation to the blue right here, everything to the right of it, when you do the mathematics, is an E field wanting to come right toward this guy, right towards this guy. Toward what direction? Well, 0 to R is positive. It wants to go to the negative direction. It's a negative E field as you move from here to the right. It's a negative E field. The more you go toward, the further out you go, that negative E field diminishes in magnitude so it's approaching 0. If you were to get closer to this thing, moving from the right to the left, as you come here, positive values, a positive R over R is a positive number, some kind of positive number. This small r minus big R is a positive number. That positive divided into a negative, this positive divided into this negative is a negative answer. Get closer and closer to it, it goes to negative infinity. Is that what's going on here too? Yeah, because here it would be R minus a number that's just a little bit bigger than R. Let me see here. Yeah, it'd be the same kind of answer here, you guys. Negative divided by positive, negative answer. Positive divided by negative, because this R is a little bit bigger. So R minus this R is a small positive, is a small negative number. Divided into here is going to go toward negative infinity. So you're going toward negative infinity as you're going, for this guy at least, as you're going with this guy, as you go from right to left. And once you get to here, it's if you come in this way, in the limit, you're going toward negative infinity. On the other side of this guy right here is pulling you to positive values, at least between the two. It's pulling you toward the positive. See, it's pulling inward here toward negative values. It's pulling inward here toward positive values. It's going in the positive direction. So here, the wire is pulling us toward in the negative direction. So the E field magnitude gets bigger and bigger, but it's negative. It goes toward negative infinity as you come to here, as you're moving up that way. It goes toward 0 if you go this way, and it goes to negative infinity on this side, from the right to the left. Over here, as you move out, you're going toward you're getting smaller and smaller values toward 0. They're all positive values for this guy because all of them pull you in here. Once you get here and you start getting smaller and smaller and smaller, you're talking about, let me just try to think of a real good way to say it here. It would be R minus R, and it's going to be 0 at that point. So like right here, from here to here, what is that? Well, how big is this right here? You're saying essentially it's R minus R. It's in the negative direction. Once you get here, well, yeah, it's going to be a negative number because small r is smaller than big R. It's going to be a negative number, you guys, but it's going to be a smaller and smaller negative number. Well, wait a minute. Negative number divided into negative number is positive answer. Hey, we said it brings it that way. You could also call it the capital R minus R into lambda, and it'll also get it there. On this side, surprisingly, as you approach it here, you're approaching an E field. On this side of the wire, you're approaching an E field that is every bit the magnitude that it was over here, but this was a negative, toward negative infinity as you're going this way. This is going toward positive infinity. The closer and closer you get to this value, you guys, you end up getting negative divided by negative is going to be a positive answer. R divided by that is going to be positive. Positive divided by positive, it's going to go toward positive infinity for this guy. Here, same thing. This is independent of these. Now when we put them together, that's going to be another story. For this right here, the closer you get to 0, it goes toward positive infinity. Simple as that. If you go on the other side of it, so it's going toward, because it wants to fire this way to positive values. If you go on this side, it wants to fire this way to negative values. It goes toward negative infinity over here. Okay, that's kind of the argument of what's going on when you're looking at something like this. Now, hopefully that explains something on that. Now, now how are we getting this? Well, you at the end of the day, this is the big thing. You've got a value here we got that value. When you add these two, oh, no, I'm sorry, forgive me. That's when we had over here for the one that was associated with, I don't know, maybe I should have color coordinated these a little bit better. I got the blue, the red, whatever. Hindsight's 20/20 on that one. But you see what I'm trying to do, guys. This is associated with the blue and how we're talking about these. Well, I got this for the blue. This one's associated, and I guess my big thing, guys, why did I go out of my way to go through the whole number line? Or at least, essentially point in that direction. I did the whole number line here. In relation to where these guys are, in relation to where this 0 is, kind of like the benchmark on this, and how you want to draw the R's, where they're going. The variable R is always the variable R, but it's a negative value if you go this way. How far you walked, we call it R, but it's a negative value when you go that way. It's a positive, the small r is positive values this way, and the same small r is negative values this way, but you still call it just R, but you just keep in mind that it's negative values that way. We did the whole thing. We looked at the entire number line essentially, and we talked about what goes on. Things tend to blow up right on the wires, but they have this particular situation and this particular look. They have it in such a way that if you're moving from one side going right onto the wire, you've got an E field that goes toward positive infinity. On the other side of the wire, you've got an E field that goes to negative infinity. Same with the other wire as well. On one side of the wire, you go toward positive infinity for the E field, and on the other side of the wire, you're going toward negative infinity as you go to it. In each case, as you're going right onto the wire, you're getting something of a magnitude that is unbounded. You get negative infinity going from one side to a particular wire, and you get positive infinity going from the other side to the wire regarding the E field. You get an E field that goes toward positive infinity or toward negative infinity, depending on what side of the wire you're on. But they're both going to be unbounded. One's going to be negative infinity E field, and the other one positive infinity E field. For both wires, that happens. Interesting. Pretty interesting. Yeah. Now that was when I just took a look at the red wire. That's when I took look at the red wire all by itself. And then I took a look at the blue wire all by itself. Yeah. What about together? Why don't you take, I don't know, the way, I'm trying to think of the notation that I was actually, you'll see this again, scroll there, guys, that I put one, that didn't really, they were just two different E fields. Just take, for the positive values, for positive lambda, you got that. For negative lambda, you got this. It was really a small r minus big R, and that was a negative R right here. But if I multiply this by -1 and multiply the bottom by -1, then this becomes lambda, and this becomes it becomes -1 times the quantity small r minus big R, which is the quantity big R minus small r. And that's the way they did it. They made it look a little easier to look at. When they did that, when you add them together, this lambda over 2 pi epsilon naught is a constant. This was the only thing doing the crazy stuff. How do they add up? Let's take this thing from, they told us to look at this and to look at it going from I think it was negative R to negative capital R to positive 2 capital R. I got a better idea. Just look at the whole number line. Look at the whole number line. Just draw a general conclusion to it. So that's kind of interest here. So let me try to, kind of debating with myself here, guys. Debating with myself here. How to actually go here. I might as well just draw this again, I think. Maybe a little easier to look at if we do. Again, I'm kind of, once again, on the fly, you guys. They didn't go into that kind of detail in the actual notes themselves, nor do they do so. As simple as that. They didn't go into the notes like that in that kind of detail, and I initially did not before I tried to do the problems. Now, again, hopefully this is a little more succinct and makes sense for us when we're doing this. And let's take a look at what we're going to do. And again, the conclusion should be rather reasonable, I think. Let me just make sure. It's a halfway decent drawing the first time, guys. I'm not quite sure it's going to be that good this time, but let's see what I can do. Okay, something like that. We got that. Okay, so we did the setup on it. Let me not, hopefully I don't have to touch this thing too much. Hopefully a lot of the challenging stuff got said, or at least in a decent manner. It's going toward positive R. So it's a right hand. It says it's positive small r, the whole thing. Okay. Here's essentially the argument. It's an important enough thing, guys, that I wanted to kind of talk about it again. I mean, we're looking at it. We're looking at a drawing like this. This is an E field of the way it's drawn. Like I said, I don't know that they could have, or I could have drawn it any better, to be honest with you. The way they got it here, we just kind of it's a little more. It's not a rigorous mathematical presentation on it, but it does give you a gut feeling for what's happening. Well, what is the gut feeling, pretty much? So, we got to really watch it, guys, and this is kind of the thing that runs the whole show, you guys. Now, you see this, you guys got the feature on the computer. You can just, bam, go back and see who's doing what. One guy's the positive lambda is well behaved in the sense that there's just a small r and go about your business and get the answer. Here, we gave a gut feeling proof as to how you can write it like this. Over there, it's a bit awkward, but capital R is a constant and small r changes toward positive infinity if you wish, or toward negative infinity if you wish. It's still called R, but the values that this small r can take, are anywhere from 0 to positive infinity and also 0 to negative infinity as it can happen. Whereas capital R is a constant. That's interesting. If something's a constant, to say it doesn't change much is an understatement. It doesn't change. So it's kind of a set value. What does that mean? It's like me saying to you, I have $100 and you have $0. Okay, I have more money than you do. Now they give both of us $1,000. The original financial circumstances were not changed. I still have $100 more than you do, but now I have 1,000 plus 100, and you have 0 plus 1,000. You have 1,000 plus 0, and I have 1,000 plus 100. I have 1,100, you have 1,000. Okay, yeah, I know the difference between us is still $100. Yeah, but let's say we started with my $100 and started with your $0, and they gave you $1 billion. And they gave me $1 billion. Well, I'm still richer than you. Yeah, $100 worth. The big thing is, I've got $1,100,000 and you have $1 billion. I don't think either one of us is complaining. The ratio of 1 billion compared to 1,100,000,000 is very close to 1. So if there's a constant R here, when the numbers get really, really big, when R gets a really, really big magnitude, the bottom gets a really, really big magnitude. And here it's very obvious with the small r. Okay, so that's some of what's happening there, you guys. So we got this, we've got all that, we put them together, and we ended up getting this. So let me, again, we have it's got the feature associated with the film. We can always go back to this stuff as we want to do it. Okay, we did a lot of stuff. We saw a good number of things. Let's talk a little bit. You always want to define things correctly. The equations have to be, got to be valid. And so you want to always, define things in a manner that's appropriate. Okay. What's going on here? How does this thing work? I mean, they're making claims here all over the place. It's an awkward graph to say the least. I'll tell you what, this thing goes down to negative infinity. This thing goes up to positive infinity. You can go over here, you're going to have an E field all the way up to positive infinity in size, and you can have an E field all the way down to negative infinity in size. You can have the R values go anywhere from this is where the 0 is. That's kind of the awkward thing. It's not 0 here. Here's where the 0 is. 0 height, 0 location for the plus lambda. I think they set it right here. So, and like I said, from plus 0, you can go to positive infinity. You can go from r equals 0, from small r equals 0. From small r equals 0, you can go to an E field of positive infinity, or moving toward positive infinity, or go toward an E field that goes all the way down here. So this goes all the way out to here toward E field toward positive infinity at small r equals 0, and at small r equals 0, depending on which way you go there, you can also get this thing going down to negative infinity for the E field. If you go here at small r equals capital R, what is capital R minus small r, where small r is capital R? Capital R minus capital R is 0. It's going to blow up toward infinity for the E field here, or blow up down this way for an E field of negative infinity here. We're saying everything in between here is not quite going to reach 0, but down here it's going toward negative infinity if you're moving that way. Here it's going toward positive infinity. As you walk this way toward negative infinity, as you walk this way toward negative infinity, if you walk this way toward positive infinity, walk this way toward positive infinity, all these are E field values they could be. As you go toward negative values of R, the further out you go that way, the E field approaches 0. Doesn't quite get there. And I said that last time in the last film, but I didn't really emphasize the idea of an asymptotic approach to E field equals 0. Here is an asymptotic approach to an E field equals 0. Here's an asymptotic approach to an E field equals 0. Okay, well, yeah, but how did they draw that? How did that conclusion get drawn? Lambda over 2 pi epsilon naught is a constant. It's a positive constant, in fact. Let's talk. I'll tell you this much. They want to add these two. You want to add these two and get the big one. This thing right here. This is everybody having been added together. It's that simple. This is the big conclusion because of an addition that's taking place. They are being added, the two E fields. So you got that right there. So as they're being added, what do you want to say about it? Well, we know that if you are here and you go to very, very, very large magnitude negative values, the E field here pushing toward negative is very small, but it pushes toward the negative direction. That guy will push, believe it or not, this will push toward the negative direction, sure. If you got to stay in the same plane. If you get off the plane here, this is another dynamic that we're not even going to explore. If we had to, we could explore it. But that's an entirely different problem at that point that we certainly could do. But that's not what we're being asked right now. So if you're very, very far away, do Gauss's the whole thing here, man. You go to negative values. If capital R, small r is a very negative number, 1 minus something very negative is very, very negative. Oh, well, forgive me. If small r is very negative, 1 over something very, very big magnitude, very negative, and very, very big magnitude negative is a small magnitude number. Sure, yeah, you go way out there, it's the way it is. You go out here, with this, in reference to this guy, also go out there. Don't go out there a distance of small r, go out there a distance of small r minus capital R, which means a negative r plus a negative value is even more negative, bigger distance. Well, that's got a positive, that's a positive E field. Yeah, this has got a bigger magnitude E field. So the negative predominates. From negative values, over on this side, you're going towards 0. So from very negative values, and you could take this thing, guys, you could take this thing and draw it out the window. And it's still not going to cross this line right here. Still going to cross this line. So as you go toward negative values, from negative values of small r, you're going to get closer and closer to 0 from a negative value. This negative guy right here is going to overwhelm this positive guy because he's closer to the action. Makes sense to me. As you go on this, so that's this right here. On this side, from capital R distance, right here, if you keep going this way, well, this guy is going to be small r minus capital R. Small r minus capital R divided into a negative lambda. Yeah, I know, but we did all that monkey business and we multiplied by -1 over -1, and that became positive lambda. You went like this. That's not a big deal. This guy right here, this r right here, this big R right here, if small r goes to a very big number, positive minus a very big positive is negative. And you can make that a negative magnitude, as big a negative magnitude as you want. Lambda, positive, divided by a very large magnitude negative number is a negative answer. What's going on here? Yeah, it is a negative answer. Because as you go out here, this guy draws you back that way. Oh, that's negative direction. It would be negative. Over here, if you went from 0 to r, not r minus r, not small r minus big R, and then that became big R minus small r, depending on all the mathematical manipulations. This is small r here. This small r going out here is a bigger number, and it's a positive E field. Yeah, there's a problem here. The positive E field in magnitude is smaller than the negative E field one and go that way. So you still got negative values. But as small r gets bigger and bigger, you get closer to 0. And that's where you're getting this. And that's where you're getting this in each case. That's where you're getting this guy running this way, and that's where you're getting this guy running that way. Okay? Yeah, it's absolutely true. What about the negative ends of this whole thing? Yeah, it really, I tell you what, let's go over here. Let's go toward small r equals 0. If you want to get close to this thing blows up toward negative. If you get closer and closer to this thing, the closer you get from the left going to the right, these are negative values, very, very small negative values. What's a positive divided by a negative? Positive divided by a negative is a negative answer. And if it's a very, very small magnitude negative answer, the smaller and smaller magnitude negative answer that you get, you end up going toward negative infinity. So as you're going from left to right, you're going toward negative infinity with this guy. Okay. Yeah, I know, but we're adding this guy too. Well, as you get closer to this guy, this is a finite value, ladies and gentlemen. This will pull you to positive infinity. Sure it will. Over here, there's a distance here, but it's a very easy distance to deal with. It's not a very big number. This is huge. It overwhelms it. So this thing is going to take you to negative infinity as you go from the left, small values, from negative values to the right. So from negative values, way out here, negative values to the right, you're going toward negative infinity. Interesting. How about on this side? Well, this side, the closer you get to it, it's positive. Very, very small positive numbers. Positive divided by positive is a positive answer. It's a positive E field and it goes toward positive infinity. Yeah, sure does go toward positive infinity. You say, well, what about this one? Well, this one's also, as you go in there, this one also draws you toward a positive answer too, in a sense. Let me look at it. You go there. Sure, this also contributes. Who cares? It doesn't contribute a whole lot. It's a very reasonable finite number. But this, as you go from the inside of all that, going to the left, you're going to positive infinity. And that's where you're getting this. All right, let's go to the inside the other way. Let's go over here. As I go over here, this has got a finite value. Positive E field, not anything huge. But this thing, you're very, very close to it. You've got a positive, let's see exactly how we're going to say this. This would be a positive number. You're approaching R. So you're approaching capital R. Capital R minus small r is 0. L divided by 0, well, lambda, remember we made it so it became a positive lambda. I'm not going to worry about that even. I'm just going to say this is a positive number, and it's going to be big R minus small r, or small r minus big R, depending on what mathematics you want to use. It's the same mathematics. It depends what manipulations you've made and what you want to use. But this right here is a positive number, positive number, positive number, and when you're subtracting, you're actually going, this big thing is big R. Here it's smaller than big R. So you're going small r minus big R is a negative number. A negative number divided into a negative number, negative divided by negative is positive. This goes toward positive infinity. On this side. What about on the other side of it? On the other side, going this way, you're going toward, as you're coming up this way, we're getting closer and closer to this. Well, this has got, look, this is a very reasonable finite number associated with this, and that's an E field that's positive. Okay, great. It's an E field that's positive. Great. So what does that mean? It's a very reasonable, not very big, very finite. It's a finite E field that's positive as you're going here. Yeah, I know. But as you're going over here, this is a positive number. This is a positive number. It's small r, the small r is that big. The capital R is that big. That distance right here is a positive number. Smaller and smaller and smaller. What is a negative number divided by a positive? It's a negative answer, and it goes toward negative infinity. I don't care if that's a positive E field. It's finite. This goes toward negative infinity the closer you make it go here. Another way to do it is capital R minus small r is negative, and then lambda divided by a negative is also. But on the other side, this is a positive divided into here. That's some of the math I did here, guys. Remember, we switched this around so we had the luxury of just looking at this by itself. You can debate how much you like that luxury, and maybe it's something we should have or should not have done. That's neither here nor there. The big thing here, guys, is we got small r divided by big R. I'm sorry, small r minus big R. Small r minus big R is always positive, and it gets smaller and smaller and smaller, but still positive. Minuscule positive divided into something negative is a negative answer. So on this side moving this way, it's a negative answer. That's where they're getting that stuff. I more or less, I think, alluded to it at some level the last time we were together, but not like I don't think the way I should have. I mean, that's kind of my argument on this thing. This will go down asymptotically, it'll never touch. Go all the way down that way. Asymptotically, it will never touch toward negative that. That same in here won't cut, it won't touch there. And this goes towards 0. And we had done some stuff on that. We had looked at this, and we've already seen this. This I did last time. When I said to everyone, why don't you get a derivative here and just see what we can talk about some of the behavior of what's going on here. Well, lambda over 2 pi epsilon naught is a constant, so that doesn't play the role, I guess. And what do we got here? Well, the derivative here with respect to r is negative 1 over r squared plus, I'm trying to give myself some room, guys, forgive me here on that. The derivative here is negative 1 over this quantity squared times negative 1 again by the chain rule. Negative 1 times negative 1 is positive 1. And you got that. If you set it equal to 0, you could divide by lambda over 2 pi epsilon naught on each side, and you got this. Solve that, play the game. You saw me play this game last time. You had the plus or minuses, and there's a lot that can and should be done, I guess, at this point. Multiply by the quantity capital R minus R squared on each side and divide by 1 on each side. You got 1. And you can look at different answers and you get like plus or minus what the value could be on this thing. You could have R minus R over R, square root each side, go plus or minus, and you can go R minus R. Equals a negative 1 right there. Well, if you kick this thing around a little bit, you multiply by capital R on each side, there's a lot to be said here, I guess you could say. If you multiply by capital R on each side, you get R minus big R minus small r equals R. Add big R on each side. Some reason I just don't think that's right, is it? No, okay, forgive me, guys. That should have. All right, please ignore that. Let's try that one more time. Let me actually look at the actual equation, because ignore this, please. Now don't ignore this, because this one's going to be right. When you are here, you kind of look at this thing, and you can look at the situation. There's a number of ways to play the logic here, I guess, or to at least bring out the logic of what you want to do. But that's kind of where I'm looking at here. I'm sorry, forgive me. It's just a 1 right here, and then you'll get the plus or minus at the end of all that. So what you're looking at is you got R big R minus that over small r, square root it, you got 1. You do the plus or minus business. So I got this. And the other one is r minus r over small r. And that's negative 1. Okay, this should work. For this one right here, you got capital R minus r multiplied by small r on each side. So you multiply by small r on each side, and you got capital R minus r is this. Capital R add r on each side, you get this. R equals, small r equals r over 2. There's your minimum. You're going to get a minimum right here. From here to here is capital R. Right here is r over 2. And that's where we're getting, I don't want to, let me draw a line there. Let me draw, that's a min point for what goes on within the two. That is going to be the minimum, right in the middle for that. There is kind of another, we did it last time. It was kind of somewhat of a surprising result, and maybe not so surprising. Multiply by, now work with this, multiply by small r on each side. Add a positive r on each side. If the distance between them is 0, these negative charges and this equal number of positive charges cancel each other out, and you got an E field equal to 0. Yeah, I think that's logical. I mean, it works. You put them together, they're going to just they neutralize each other. There is no E field. There's no net E field if they're together. So that's of interest right there when you're playing games like that, you guys. So that's a fascinating matter in its own right, you guys. Okay. We got that. We're looking at all this stuff. Another thing of interest, I guess, in the whole matter. And again, I've more or less went in this direction, albeit not very well. Hopefully this is better for you guys. The last time. Last time I've gone in this direction. Last time I had gone in this direction, I don't think as well as it could have been done, but hopefully this is a little bit better for you guys. Hopefully this is somewhat better, help you out a little bit. Well, you got this right here. What's going on here? What is this about these derivatives to begin with? Well, look, there's a lot you can learn here. The derivative tells you the instantaneous slope somewhere and how its tendencies go and everything else. If I took a second derivative, I could confirm that things are concave upward or concave downward or whatever. What else could be happening here? There's no concavity if it's equal to 0. But if the second derivative is positive, then it's concave upward. It's going concave upward if the second derivative is positive. If the second derivative is negative, it's concave downward. So concave downward, if second derivative is negative, let me look at it, make sure I'm not going to feed you a bunch of lies as well, you guys. Right. If the second derivative is negative, it's concave downward. If the second derivative is positive, it's concave upward. Well, we don't really need to go there quite. We can just say, okay, well, we can certainly confirm this when we're doing this stuff and take further derivatives on this. But let's just stay where we are right here. This might be sufficient to at least give us some more insight on the whole matter. Look, can we at least say this much? This capital R minus an R, let's sort of talk. If R is a very big magnitude number, if R if small r is a very, very big magnitude negative number, let's say. Well, if you square a negative number, you get a positive answer. If you square a negative number, you get a positive answer. If you square a negative number, you get a positive answer. If you square a positive number, you get a positive answer. And if there's a real big magnitude r here, when you square it, it's a huge magnitude. -1 divided by something huge magnitude is a very, very small magnitude negative answer. Good enough for me. Come over here. This big R is a positive number. If you subtract R from it, if R is on the positive side, if you deal, let's actually be very, very careful when we do this, and maybe we can see some stuff here as to where these slopes are going. If we're going to deal with very big positive values, a very big positive value of small r squared is huge. -1 divided by something huge is a very small negative number. This will be a positive number that's very small, and then there's a tug of war here, and maybe we can discuss it. If this is positive, if big R was 0, 0 minus a positive r is just negative r. Negative r squared would be as big as, the quantity negative r squared would be as big as r squared. And then they just cancel and be 0. This guy, however, doesn't let it go as negative. So when you square it, it is a smaller magnitude number. A smaller magnitude number divided into 1 is a smaller magnitude number than this magnitude. A smaller magnitude number divided into 1 is a positive number that's very small, but it's got a bigger absolute value than this one does. It's always going to be a bit positive. It's always going to be a bit on the positive side. So what we're looking at is, let me try to think here, guys, exactly here. R equals 0. There's got to be a way here, guys. I'm looking. Oh, okay, no, this is fine. This is actually fine. So what is happening here? This is always going to be a tug of war that the positive number wins. It wins it by less and less and less. The slope goes towards 0. As you go in the positive r direction toward infinity, our values get bigger and bigger and bigger positive values. This derivative approaches 0. This thing starts to flatten out and almost hits a slope of 0. So it tends to want to, in the limit, this thing is flattening out, and it never gets any bigger than 0. The negative. Yeah, but the slope, however, is always positive. So this is always I don't want to draw too much on it, guys. That's a positive slope. That's a positive slope, and that's a positive slope, and the slope goes towards 0. Okay, it's flattening out. I can see that. What about toward negative values? A very big negative value squared is huge. Go into here, you got a negative number. Yeah, a very big negative value here for R, a very big negative value for R, and then go positive R, positive capital R is what it is, positive. Positive capital R minus a negative is a little bit bigger. If it's a little bit bigger, when you square it, this is going to be a small positive number, and this is going to be a positive number that has this is going to be a negative number that has an absolute value that's bigger than this guy's absolute value. The net is negative. Now wait a minute. Over here, the whole thing was positive, and it went towards 0. The derivative went towards 0. Here, the derivative will also go towards 0, but that's a negative slope. Remember, upward to the right, you guys, is a positive slope. Upward to the left is a negative slope, and it becomes less negative as you proceed. Yeah, what happens right here at 0? You know, this right here is, you know, I don't want to write too much on this, but what the heck? I mean, we didn't do it last time, so do it now. Here's 0, here's capital R, and here are the distances under consideration that we talked about, and you're going right here, you know, right there, and that was that length right there, and that got you to here. Put a 0 in here. Well, yeah, put a 0 in here, but how? You know, how are we going here? How are we doing this thing? We're saying it's very, very, you know, as the numbers are less than 0, as the numbers here are less than 0, it's always going to be a negative slope, but the negative slope goes toward negative infinity. The negative slope will go toward the fall down being, you know, like I said, you run and it falls, it's going to go toward negative infinity. You run this way and it falls down to here. We'll get over here. Run this way, fall down to here. It's going to be negative. If the r's are approaching from negative r to 0, from very, very negative values going, well, if this is still a negative value, you square it, yeah, you get a positive, you know, you get some kind of positive answer. The negative 1 divided by this is something huge, you know. As you go there, let me see, as we go here, let me just talk about it, guys. Let me make sure I got the right thing here. Okay, right. And over here, it's a different dynamic. Here you're going toward r minus r here, that's 0. The small r is 0. Capital R minus 0. Capital R minus 0 is capital R. Capital R squared is something. It's a finite number, guys. Yeah, this is not a finite number as you go towards 0 from negative values. It's a positive answer on the bottom. Negative divided by positive is negative. Oh, it's a negative slope. This thing starts sloping like this. That's still a negative slope. Runs this way, falls down. Go on the other side. Let's go from big R onward. As you go to big R, put a big R right here. Well, that's not really a big deal. Big R squared, negative 1 divided by big R squared is, yeah, it's a negative number. True, it's a negative number. Why don't you put a big R here? It's a finite negative number. Why don't you start putting a big R right here as you go from positive values? As you go from numbers that are, as you go from R values that are, you know, like I said, R, you go, well, hey, the R values are big. Yeah, who cares? Big R minus a small r that's a bigger number than capital R, and it is. This is the big R here. This is how big R is. This is how big R is, and this right here is, forgive me, this is how big R is right here, and this is how big small r is over this way. Well, that's fine. This minus this is negative. Who cares? Square it, it's positive. 1 over this is a positive answer. This is a positive slope going up that way. Here it was a negative slope. Here it was a positive slope. Yeah, as you go from big numbers to small numbers, it's a positive slope. This one also is a positive slope, just like this one is. And this one is a negative slope. It's a negative slope, just like that one is. And if you plug in, you know, when you actually plug in the limiting values, you're getting, you know, it doesn't matter if you're approaching this from the left or from the right, the slopes are both positive over here. And here it doesn't matter if you're approaching from the right or from the left, the slopes are both positive. Here, forgive me, not positive, and positive magnitude, but that doesn't mean anything. These are negative. So it doesn't matter if you're approaching this from the right, or if you're approaching this from the right, or if you're approaching this from the left. Negative slope here, approaching from the left. Negative slope here, approaching from the right. Both negative slopes, whether you're approaching from the right or whether you're approaching from the left. Here you get positive slopes, whether you're approaching from the left or whether you're approaching from the right. Now, the actual values, I didn't say they were the same. Yeah, the slopes are the same. This, as we've got it set up, this one's going to negative infinity. This one's going to positive infinity. Regardless of the slopes of this interesting symmetry with the slopes. They're equal magnitudes. Negative slopes here, positive slopes here. Yeah, on this side going to positive infinity. On this side going to negative infinity. On this side going to positive infinity. On this side going to negative infinity. Okay, so there's more on that. I mean, this is a fascinating problem, guys. It doesn't. Neither I nor the answer key did justice to it the last time I talked about it. I mean, hopefully there's something there, though they've done the answer key that let me qualify that. I mean, the answer key that we're able to use as teachers is outstanding, and all the huge number of problems that get solved for this textbook that we use are very impressive, and they do a great job. I certainly could have done better the first time when we looked at this. So I hope this helps you guys out. All right. Thank you for your time, guys.